Okay, so let's get into our first example of an addition reaction. The simplest one and the exact opposite of an elimination is hydrohalogenation, right? Because we're going to be adding a hydro and a halogen, right? Hydrohalogenation. So we're going to use for hydrohalogenation these three. We're not going to use HF. So HCl, hydrobromic acid, and hydroiodic acid. So if we do this at cold temperatures, then we get a pretty good yield of addition. Now, if the alkene, this ones we've considered at this point are symmetrical, right? There's a hydrogen here and there's a hydrogen here. So if the alkene is not symmetrical, then you need to appreciate that there are two regioisomers that are possible. We might either, so here's one that's asymmetric, right? We might get the halogen over here, or we might get it alternatively on the other side, right? So the question is, where does it go? Well, it turns out that hydrohalogenation is regioselective for the Markovnikov addition. So in 1869, hard to imagine how they had the technology to appreciate this then, but in 1869, Markovnikov observed that the hydrogen atoms tend to add to the carbon that already has more hydrogen atoms on it, okay? So if you look at this structure, this one already has more hydrogen atoms on it, and so the hydrogen atom is going to go here, and the bromine is going to go here, right? And that's what this is. That's what this shows right here. The halogen is generally installed in the more substituted carbon, but it doesn't matter how you appreciate that. It might be easier to think of it as the hydrogen goes where there's already more hydrogens. It's looking for buddies, looking for friends. Okay. Now, if we do HBr in the presence of peroxides, which we're typically going to just do ROOR, okay, where there's no alkyl groups. If you do it in the presence of peroxides, you get the opposite, anti-Markovnikov addition to a high yield. All right, so the reaction mechanism is different for the peroxides. That's supposed to be an ROOR. It's different for peroxides, but we're going to look at the mechanism for Markovnikov addition. The peroxide mechanism we're not gonna study here. All right, so here's the mechanism. It's just exactly well, we actually got a preview of this in a previous conversation, didn't we? I think in the introduction to addition reaction. So first of all, pi electrons act like a base, right? And so this comes in, and there we go. And when the hydrogen goes to the atom that's already got more hydrogens on it, and then we get a carbocation. And boom, there's the nucleophile, okay? And it's that simple. So it's a two-step reaction. And so you've seen energy diagrams like this before. Here's the intermediate. Since this is two-step, you know there's an intermediate. The first step is the proton transfer. And the second step, this is the slow step, right? You can see that's the activation energy for that one. The activation energy is a lot higher for that than it is here, right? It's a small activation energy. So the slow step is the first step. And the second step is the nucleophilic attack. All right, so recall that there are two possible products, Markovnikov and anti-Markovnikov. Let's probe what the anti-Markovnikov would look like if these pi electrons go and attack that, and the hydrogen went to the side with the fewer hydrogen atoms, then you would have a secondary carbocation, right? But if in the Markovnikov pathway, the hydrogen goes over here to the carbon that's got more hydrogens, because that already has a hydrogen on it, right? So this is the second one, right? So if it goes to the side that's got the more hydrogens on it, then you get a tertiary carbocation, which is more stable. Oops, lost my place. Okay, so the more stable tertiary carbocation, right? But the transition state is also lower, right? And so it's faster. It's got a lower activation energy. Okay, hydrohalogenation, you also have to appreciate it could result in a chiral center. So let's look at this. If you already have a hydrogen here and then two hydrogens here, right? Okay, and HCl goes here. So the hydrogen's going to go here when this double bond goes away, and this is going to be chlorine. Well, now we've got an ethyl group, a chlorine, a hydrogen, and a methyl. So we have a chiral center now. There's our chiral center. Since it's chiral center, we're actually going to get both the R configuration and the S configuration, and we are going to get it in a 50-50 mixture, okay? They're formed in equal amounts. This is called a racemic mixture. Racemic mixture. Okay? And this is the reason why. We're going to get both because the tertiary carbocation intermediate is flat. And since it's flat, then the nucleophile can attack either from the top side or the bottom side, and it's 50% probability it's going to be on one side or the other. Equal probability, all right? So half of them are going to go to the top, and half are going to go to the bottom, and so we're going to get a racemic mixture. Now, also, you need to remember that carbocations can rearrange. So if we have, in this case, we have the chlorine's going to, let's see, the hydrogen is going to go, because remember, the hydrogen goes first. So there's the hydrogen right there. There it is right there. We're going to get a secondary carbocation. If we get a hydride shift, then we're going to end up with a tertiary carbocation, right? And that's exactly what's going to happen. So after we get the tertiary carbocation, the chloride goes there. So you got to be careful. You can't just put the hydrogen here and the chlorine here, because when you can get a carbocation, when you can get a rearrangement, you will get a rearrangement. When carbocation rearrangements can occur, they do. Okay? So it turns out it's not going to be 100%, but you are going to get a significant portion that are going to be rearranged. This you need to play with. That reaction you need to predict. You need to cover up the products with the one side and predict what's going to happen. It'll help you practice your rearrangements, help you practice your electron pushing arrows. It'll help you practice your addition reactions, and it'll remind you that sometimes there's really subtle things that happen in these reactions, and we have to be ready for them. Okay, good luck.